Hey everybody, happy Tuesday. All right, we're on to, oh goodness, yeah, there we go. That's right, I posted the new project already. So we got the project solution for project 2 to talk about, and then we'll get into heaps, priority queues and heaps if we've got time. I think this will probably take most of today. We can save priority queues and heaps for Thursday. If that works out. I think that should be pretty good here. So let's talk about our linked objects project. Let me fire up PyCharm here. No, I don't want to search for it. No, goodness gracious. I don't want that one either. I want PyCharm. There we go. We'll see. I should have closed some more tabs here. I was watching a fun little silly playthrough from Baldur's Gate 3. Apparently they beat the game with True Strike, and I was kind of curious. That was kind of fun. So I'll watch that one more later. All right, so let's do a new project for, this was project 2 linked objects here. And again, this was the idea of using the term nodes, which is a single monomial, to make up a polynomial. So instead of using a linked list itself, our classes were going to be the link here and store that. So we're going to have to build some classes out and have a little bit of fun with it here. So we're going to have a class for polynomial. Right, and polynomial has a couple things here, and then inside of polynomial, right, we're going to have this private helper class for the term node here. So the term node class then has some details, right, with the exponent, a coefficient, and the next term here, and we need to have the equals and not equals functions. So we can probably need to do those separate. So we'll have a init method that probably takes the coefficient, and the exponent here, and then maybe even the next value, and we would next defaults to none until we know otherwise. Coefficient, I didn't spell right here. Let's see what our suggestion is. Typo, rename to coefficient. There we go. All right, I like it. So self.coefficient is the coefficient, and self.exponent is the exponent, and self.next is the next. Right, pretty easy for this one here. What does it not like? Oh, build shadows next, that's fine. Should be okay here, right? And then we need to figure out if we're equals. So our equals function here that takes another term node. We're going to return self.coefficient equals other.coefficient. Right, just compare our coefficients and our exponents. And self.exponent equals other.exponent. So I'm not really comparing the next terms here, because I only want to be able to compare one term at a time, essentially. Right? And then once we have an equals, our not equals then is not self.equals other. Right? We already know the equals. We don't need to do work for the other one. Okay, so then for a polynomial then, we said polynomial should take a coefficient and an exponent. So this will have the first term automatically here. So we're going to take a coefficient and an exponent for the first term in a polynomial here. So this needs the first term in the list. How's it going?
Hello, sir. Sorry about that.
Oh, no worries, man. It's so nice out today. I love it. Love it. The weather,
yeah.
The sunshine, it feels good.
It's really good.
Feels good.
Tropical weather.
Yeah. So our first term, then our first node should be marked as private here. So this will be our first node. First term, first node, sure, first node is going to be a new term node, right? So we're going to create a node, term node. Do we call it term node? Yeah, term node, given the coefficient and the exponent. So it'll be self.term node. So I know what the first node is, given the coefficient and the exponent, and there is no next term because I'm a brand new polynomial, I'm just a monomial. I haven't added anything here yet. So I've got the first here. Right, that's in my init. Then I'm going to have to do add, multiply, differentiate, integrate, and turn it into a string here with coefficients to 2 decimal places, equals and not equals. Now with this equals and not equals, I need to look at every term in the list here to make sure I'm equal. With term node, I just said, hey, do my coefficient and exponents match? I'm just looking at a single term here. I'm not looking at the entire chain. If I want to know if polynomials are the same, then I can figure out all that linking here. What does it not like about this one? Probably the number of spaces, right? There it goes. Okay. So that's the basic here. Now add, multiply, differentiate, and integrate. I think add will be the easiest one to start with here. So to add, So to add another term, another polynomial to this one here. The idea when we add polynomials together, right, we're going to take each term in the other polynomial, add it to mine. But remember we said when you add two things together, you don't actually change the original. So we're going to make a new polynomial that has all of these original ones here. And this is where it gets to be a little bit tricky. So to do this, what I want to do is have a helper method that adds a single term at a time. So you could do it lots of different ways, but I think this approach is probably the easiest sort of cheating approach here. So I'm going to add a helper method for add single term node. Term node. That takes a term node to add. Term node to add here. So if I have a polynomial and I want to add a single term node to that polynomial, I'm going to start at the beginning node and I'm going to see where it fits, right? Because we want these in descending order. So if we just keep them in descending exponential order, life is easy. I don't need to worry about trying to do this just when I want to turn it into a string, and it makes adding so much easier here because I only know what the next is. So I know if my exponent's bigger, I go first. If my exponent's the same, I just combine coefficients, add coefficients, and if my exponent's less than, I just need to go to the next one, right? Until I find where I'm going to go in this list here. So to add a single term node then to a polynomial, I'm going to check to see if it needs to go first. So this will be a polynomial that is changing here is a little bit interesting. But again, when I add, I'm not going to change my original. I'm going to make a new polynomial and just start adding all of my terms and adding all of the other terms. Is sort of my strategy with this one here. So adding single term node is a private helper method. No one else should be using this, so it's fine if we change terms here. So we're going to say, hey, if the, so I want to check if the coefficient, or I'm sorry, if the exponent is larger than mine. So if the term nodes dot exponent is greater than self dot first nodes exponent. Okay, yeah.
So for that one, that's the polynomial class, right?
So in polynomial, this is a private helper function that lets me add one at a time that I'm going to use to be able to add all of them. Yep.
So like what I did was in the init method, I just set self.add to none, and then to add the single term, I would first confirm if that's the head one. Otherwise, I would just append and set the new one to point to a none.
So so if you're not tracking the exponents descending order first, you can, but we also need to check to make sure we don't just append if the exponents match. Because you don't want to have two, because then we'll have to clean those up later. It makes more work for us. So I think this is, I mean, there's lots of different ways to approach it. I think this will be the least amount of work, which I like. Again, lots of different ways to go about it. As long as we're getting the job done, that's great. But this is just kind of thinking through how we want to approach these. So if their exponent is more than mine, right, I know that they're going to need to go first, and then my first can go next, right? Because I want to keep these in descending order. So I'm going to take that term, because I know it's just a single term here, I'm going to make a new term node off of their values and add it as my first. So I'm going to take my first node, I'm going to keep my first node, so old first will be my self.first node, right? And then I can change my first node to be a new self.term node, given the term nodes, is it coefficient? I think coefficient first, coefficient, and then the term nodes exponent. So I'm going to make a new first, given these, and then I can set the self.first nodes next to the old first, right? Because I know my exponent was greater. So now I have a new first node, and then everything that follows that is what used to be my first node. And that's great, we're done because I've added a single term. If that's not the case then, right, so if my term node, that exponent is equal to the self.first node's exponent, then I'm just going to go combine coefficients. So we'll take my self.first node coefficient, and I'm going to add to it the term node's coefficient. That's all I'm going to do, and then I'm done. So I've either added it to the start, I've combined it, or now if it's less than, now we need to see where it needs to go. So this part gets to be a little bit tricky. So my else case then, I need to start finding the next term that this will go. So I'm going to do this sort of walking process that we did. So I'm going to have the current term node will be the next one. So first node's next. So self.first.next. because I know it doesn't go before first, so I need to see where does it go before, because I need to stop before so I can make all these next links work as I'm going here. So the current node, if it's going to go before the current node, right, then I need to change the current node's next to be the new term, and then take what was after that and slot that one in. So I'm either going to find a match or find where it's greater than, right? So if it's greater than the next node, then I'm good. I can put myself in between. If it's the same as the next node, then I can just add the coefficient. So using this current term node, so I'm going to say, well, my current term node does not equal none, right? Because I might hit the end. If I hit the end, then there's nothing left to do here, right? I need to become the next one. Actually, so I think I need to work this off of the next one, sorry. Well, the next is not none. So let's start with the current, start with the first node. So the current term nodes dot next is not none. So as long as there's something after my current term, I can keep looking. As soon as I run out of things here, then I'm just going to go add myself at the end, because my exponent must have been less than. So if I have a next, if it's not none, then I'm going to check to see if my current term, the term nodes dot exponent is greater than this next node's exponent. If it's not none, I know it's there, exponent. So if I'm greater than that one, so I know I can't be greater than the first one because I can't have gotten here, right? But if I'm greater than its next, I'm going to go in between. Yeah?
I'm sorry to interrupt you. You are checking for the exponent of the next term node.
Yep. So checking. So I know that I'm not greater than the first. So first will be my current. So now I need to see, do I go between the first and the second, or the current and the next one? So I'm just going to keep walking. Hey, if I'm greater than the next one, I go in between. If I'm not greater than the next one, I need to keep on moving or see if I'm equal, right? I'm going to have those two cases. So if my term node's greater, then I'm going to be a new term in between these ones. So then I can say my term nodes, the old next will be the current term node's next, right? To keep that term node there, then my current term node's next will equal a new self.term node, given the term nodes, right, this term node to add, right, this one here. We'll make a new term there in between, right? And then I can say, okay, the current term node's next, this new one I just created, that one's next, then is the old next. I just put myself in the middle, right? If I'm not greater than, I need to see if I'm equal. Oops. So if my exponents are equal, then I can combine. So then I'll take the current term node's next coefficient and add to it the term node's coefficient. And then we're done, right? Life is good. Otherwise then, now we need to go to the next one, right? If I'm not greater than I'm not equal to, now current term node needs to go to the current term node's next. Okay, walk to the next one. And then if it's not none, check if I'm greater than or equal to, go to the next one. If it's not none, go to the greater than or equal to, and then, this needs to break the loop, right? Once I've done that, I need to be done, so I can break my loop here, I can break my loop here. Right? Stop the loop, stop walking, because I've already added it, right? I've either added it in between, or I've combined my exponents, I'm done. And then the entire loop then has an else. If I've gotten through and I didn't break, then I ran out of terms, and I know my exponent must be less than, right? But my current term node next is none. It is none, so I can set the next of it here to a new term node. Right? Because I ran out of nexts, but I know I'm not greater than or equal to. So I must be less than, I must be less than, I must be less than. So eventually then I just fall to the end. So I should be able to add a single term at a time, and really the entire logic of the project is here in this add single term node. That's it. You're going to see the rest are super easy now that we're just going to cheat here. So that's all that one goes. So once I can add one single term node, I'm just going to repeat this process over and over and over and over and over again with all of my terms and all of their terms. So to add then, I just want a copy of myself. Or I find I can add one at a time. Right? That'll work perfectly fine. And I'm going to add all of the others to it here. So I'm going to have a new polynomial. Polynomial is a polynomial given, I'm just going to go my first term. So self.first nodes coefficient and self.first nodes exponent. Right? So brand new polynomial with my first node's coefficient and exponent. Now I have my first node, and then I'm going to have my next node after that and keep on going. So my next node to add will equal self.first nodes next. And while next node to add, next node to add is not none, then I can keep on adding. So I'll take my new polynomial and I'm going to call the helper add term of the next node to add. So if I have a next, or while I have a next here, right, keep on adding them here, and then my next node to add equals the next node to add dot next. I keep on going to the next. So I'm going to go to the node level and just keep on adding one node at a time, one term at a time, one term at a time, one term at a time here, which is fine. It ignores all of my links here because I don't need any of the links, right? I'm using the links here, so all I'm going to do is go and add one term at a time to myself, right? I never look at the term nodes next, as I'm just treating that as a single term, because I want to add a single term node. I don't want to add the rest of its baggage here. When I want to add polynomials, this manages the links of here's the polynomials next, and next, and next, and next, and next, and next, as we go. Oh man, my sugar's getting low. I might need to go get some Coke in a minute. We'll see. It might stabilize. So that's all. This adds all of mine to that new polynomial. Then I'm going to say the others polynomial. So the next node to add is going to equal the other dot first node. Right? And then the same loop here. While that next node to add is not none, keep on adding it, and it walks to the next one. Right? It just starts at the others first node, which is saying, oh, hey, you're accessing a protected member, which is fine. I'm in my class. No worries here. So just keep on adding the others first node, and then next and next and next and next and next. As long as I have next, let's keep on going. When I'm done, then I can return the new polynomial. Right now I've added myself and the other polynomial together, and I've returned a new polynomial. So I haven't changed mine. I haven't changed theirs. I've grabbed their term, one term at a time, added them together. So now I can add. So we should test it out, make sure that one works, right, before we get too far here, right? So we're going to make a polynomial, or we'll say first is a polynomial given, what do we, like 2x to the third, right? And then the second should be a polynomial given, I don't know what, 3x to the fourth or so. And then I should be able to add them together, so then the result should be first plus the second. And because I have overridden the addition operator, I can just add them together like this. Yeah?
Because like I kind of assume that the person creating the polynomial will use the highest coefficients first, the highest exponents first. So first I iterate through the two polynomials at the same time to find the matching exponents. Mm-hmm. Then I add them like one at a time. So first, if I run out of matching exponents, I just add all of the rest, the first polynomial and the second one. I don't know.
So you go and find the matches first?
Yeah.
Yeah, I mean, that's definitely one way to do it, and then you know the next ones will be there. Right? And we know our polynomials are in descending order because we make them in descending order, and we control that. So I think that would definitely work. Feels like an extra loop to go find matches, I think, but then the rest of it's easy, right?
Oh, okay.
Yeah, I think either way will get the job done. So if you want to go combine like terms first, and then just boom, here's the rest, sure, that definitely works. I'm just leaning on my add single term node, takes care of that for me, right? So all I have to do is go add all the terms and add all of their terms, right? Oops, I don't want to drag that was bad. So I can't print these yet. Yeah.
What do you press to go back?
I'm sorry? Undo. Control Z is undo. Yeah. So that's, or you can go to the edit menu and go undo. That's Control Z.
I wish I knew all these shortcuts.
Oh, I'm sorry. Yeah, there's so many shortcuts I take for granted, for sure. Now, so to print these out, I probably want to define that string representation, right? So a string, then I'll have my, I don't know, result starts as nothing here, and then my current term, current node equals my self.first node, and while current node is not none, I'm going to take my result, I'm going to add to it here I want the whatever coefficient x to the power to make this look pretty, and I was going to round those off at 2 decimal places. Right, so we're going to take a formatted string of the current node's coefficient, and I want that as what, 0.2 decimal places, 0.2f or something like that. I feel like that was probably the syntax, right? X to the power of then my current node's exponent. And I want to probably add in a space here. I can't really string join these together, or I could go put them all on a list and then use string join if I wanted. That might be pretty easy. Maybe I make a list of terms and then join them all together, or this is probably fine if I've got an extra space at the end. I don't really care if there's an extra space here or not.
Yeah, I feel like that. So I like, instead of having the string one, I just create like display method.
Okay.
So I put like display and display that.
Yeah, so overriding functions of the operators is the better way to do it. That's the more idiomatic way in Python. Right? If we're going to add things together, I'm going to add the override add. If I'm going to turn them into a string, I'm going to override string. You can write the other methods and other functions to do it, and it gets the same job done, but this is probably the more proper way and the more common way you'll see. When I'm done, I can return my result. So I should be able to print all these out then, right? So I should be able to print the first here, I should be able to print second, and I should be able to print the result. Second, come on, there we go, and I should be able to print result when this runs. So I should have 2x to the third. I forgot to move current node, right? I always had an infinite loop there. So current node then equals current nodes.next. There we go. Then I can return the result when I'm done. I shouldn't loop forever. Yeah, 2x to the third, 3x to the fourth. Oops, I forgot the plus signs here, right? So I should do probably plus. All the other ones. Oh, now I have an ending plus at the end, and that's sad. I'm sorry?
Like the comma and the equals to quotes. Just so I can keep it kind of appending one after the other. Just in terms of strings.
Yeah, I'm just using the plus equals to just stick them all together at the end. So if I want to take off that last one, then I can return a slice of that to -2. Take off the last 2. There we go. That takes off the last. Oh, I guess I want a space and a plus. Make that a little prettier looking. Okay, now it separates them, right? So 3x to the fourth plus 2x to the third. So that one works so far, right? So then I should be able to take another polynomial, maybe third is a polynomial, and let's have something that's going to have the same exponent. So maybe 3 x to the third. And now I can take the result, I don't know, fourth then will equal result plus the third. Print the fourth. I forget, I had the sample ones here, but I just want to see if this one will go. So, oh dear, it failed. So somewhere in result plus the third, it failed. So in add, in the add single term, while current term node next is not none. Return self as other. The coefficient none, so you can't compare if it's none. So I was checking if something equals another at this point in my equals function. So somehow I was checking to see if the term equaled itself. Where did I do that? That's super weird. When I was checking if it's not none, term node is not none. Checking to see if that's not equal to none. Oh, because I was overriding that one? Sure. Okay, that's super weird. But so I can't check if other is none, return false. That seems weird here, but sure. Let's see if that fixes it. Okay. So somehow I was checking to see if one term equaled another term, but the term was none. Sure, I guess. Okay, so that did combine. Right, my fourth one here, a 3x to the third, added 3 more to my third. Seems to be good so far. What if I want to add 2 different ones together here? So let's add a fourth and a fifth, or we'll add some more. I don't know, fifth. It's equal to polynomial of 5 to the 7th, and 6th. It's a polynomial of don't know, what's 7 to the 9th, and then a 7th is going to be 5th plus 6th, and then, I don't know, a 9th or 8th. I'm running out of numbers here because I'm getting confused here. Will be 7th plus 4th. Right, 2 different polynomials eventually here. Good, I should probably name these things better. And then print either, oh my goodness, 8th. 8 E-I-G-H-T? 8th? E-I-G. I can't even spell. How do you spell 8? E-I-G-H-T. That's 8. So then is that one? My goodness. Terrible in English. I apologize. All right, 7x to the 9th, 5x to the 7th, 3x to the 4th, 5x to the 3rd. I think that's what we expected here. Again, some unit tests would be cleaner instead of me just eyeballing this, but I was feeling a little bit lazy at the moment here. We didn't need any unit tests, right? We just had to have the functions work. So I've got term node, I can add, I haven't multiplied yet, I haven't differentiated, I haven't integrated, my string seems to work, polynomial equals and not equals I haven't got to yet. We're getting close, right? We're set the stage for this, right? So now I can do string. I think string works. So now that we can string, now let's look at multiply. So we want to define our multiplication. So with multiplication, right, we have to FOIL my first term times every one of their terms, plus my second term times any one of their terms, plus my next term, right, on as many terms as I have times all of their terms. So we're going to get this interesting result that we're going to start adding stuff to. So my polynomial, my result will be a polynomial, and the first one then is going to be my first times their first, right, as we go. Then we can keep on going, or depending on how we want to figure this out, right, we're just going to keep adding a bunch of terms together. So the first one here then will be my self.first node. Now, when we multiply polynomials, right, we are, what is it, we multiply the coefficients and we add the exponents, or, so the coefficient then will be my first term node's coefficient times the other's first node's, dot coefficient. That'll be my coefficient, and then the exponent will be my self.first node dot exponent plus the other dot first node dot exponent. Exponent, that sounds probably right. So that'll be the first term that gets created. Bless you. Right? It doesn't change mine, doesn't change theirs. And then as long as they have more terms, I'm going to multiply my first term times that. Right? So my current term will be self.first term node, right? And then so while my current term is not none, I'm going to keep on going, right? And then I'm going to start with their next term. Oh goodness, I think this is a little bit messy. So maybe I want to cheat here. So my first term is not none. I want to start at their next one. So their current term, or other current term will be the other first node. And while the other current term is not none, I want to keep on making, what is it not like other for? Why is it red? Other. Create parameter other. I have a parameter other. That's my parameter other. Okay, I think it's just confused here. So as long as my term is not none, as long as their term is not none, we're going to keep on going. So I'm going to make the next term, I guess. Yeah, so the next term then will equal the my current term dot coefficient times the other current term dot coefficient. Right, and then the next term will be self.term node of the my current term's coefficient times their current term's coefficient. Right, then the exponent, so my current term's exponent plus their other current term's exponent. That makes the next term, right, that I need. Then the other current term needs to go to the next one. Equals the other current terms next. Walk to the next one, right? Or I got to add this in. So my result then, goodness, why is it still not like other? Am I missing something? Other first note? I'm not sure why it's red. Sorry, my sugar's low. All right, almost done. Almost out of inset. All right, so the next term that we create here is then. So now I'm going to have that result. So if I don't have a result, it's the very first one. This is where it gets a little bit messy here. So I can take one polynomial. Yeah, so my result. Equals none. I can probably start as none. This might be easier, so I'm just going to keep doing the same math here. So if my result is none, then my result will equal the polynomial given the next term's coefficient, the next term's exponent. If it's not none, then my result already is a polynomial. Then result.add single term given my next term. Right, so if I don't have a first term, right, if I don't have a result yet, then it will be the polynomial of that first one. Otherwise, I want to add this new term I just created. I want to add that single term to the result. Right? And I'm just going to keep on going until other current term is none. That will do all of the other current terms. Eventually, when that one's done, then my current term needs to go to the next one. My current term's next. Right? So I'm going to loop for every one of my terms, right, starting at my first one. I'm going to go starting at their first one, do the multiplication here, add that term. Should be pretty easy. And then mine will walk. Once theirs is gone, I'll go to my next term. When I'm done, then I can return the result. Great, so I think that'll work for multiplication, right? So I just multiply the coefficient, add the exponents for every one of my terms, for every one of their terms, and then just keeps on going with these two loops. So let's try that. So I should be able to multiply two polynomials together then. So if they're single term monomials, I'll just get one back. But if they're two, right, 2 times 1, I'll get 2 terms back. If they're 2 and 2, I should get 2 terms times 2 terms, depending on where the exponents go. Right? So if we kind of FOIL those out ourselves, 3x to the 4th plus 2x to the 3rd times 3x to the 4th plus 5x to the 3rd. I'm going to get a bunch, so 3 times 3 I'll have 9, x to the 8th, and then 15x to the 7th, and then this one is 6x to the 7th plus 10x to the 6th, and those should combine. Oh man, I have to write all this down here. I think that's why I had the example, right? Did I give you that example in here? There we go. Whew. All right, let's just keep our example here. That'll make life a lot easier for us. That's what I should have done in the first place. So poly 3 is 2 times 1, right? 2 times 1 was 2. Yep, so I should get those, and I should be able to print those out, right? So print poly 3, print poly 4, and print poly 5. So I don't have differentiate and integrate yet, so we only have multiplication. So, we've lost our lights here. Comment those out for a second. So I should be able to get 6x to the 7th plus 4x to the 6th when I multiply those two together. Let's see if that one works for us. Oops, others, first node. Oh, that's why. Okay, did I have a semicolon? That's why. Goodness. Okay, it was mad because I had a semicolon. There we go. Hopefully that one works now. Let's see. All right, so 6x to the 7th plus 4x to the 6th seems to work so far when we multiplied. Right, so now I have two terms, right? Poly 1 is 2 terms, poly 3 is 2 terms. So if I wanted to multiply those ones together, I should get another result. I don't actually know what the math works out to be, but I feel like we're in pretty good shape if that one's working based on what this was here. Right, and again, we're just kind of using all of this whole, I can add a single term at a time that we wrote first. Right, because I just keep adding single terms here. It will combine the exponents for me as I go. It just keeps on going. I just use the two loops to make sure I get all of my terms times all of their terms. Right, and then we can do our differentiate, define differentiate. I can't even spell that here. So for differentiate, then right, I'm going to return a new polynomial. So I'm going to have a new polynomial result. Right, so my result will equal a new polynomial. And the first one then is going to be self.first node dot coefficient. And when we differentiate, oh my goodness, I have to remember how this works here. We take my coefficient times the exponent, and then I take the exponent minus 1. Right? Because this was 6x to the 7th, and now I have 42x to the 6th. So the coefficient will be the current term node's coefficient times the first node's exponent. That's the new coefficient. And the new exponent then is self.first node's exponent minus 1. That's the first one. And then while I have next nodes, I just keep on adding them. So that's the first one here. And then the next term is self.first node's next. And while next term is not none, I'm going to take my result, which is a polynomial. I'm going to add a single term of the next term's coefficient times the next term's exponent. Coefficient times the next term's exponent. And then the next term's exponent then is going to be my next term's exponent minus 1. Right? That'll be, I'm sorry, I want a term. So self.term node of current next term's coefficient. I guess I should call that current term. That's ugly to be next term. Sorry, let me rename that. So, factor rename. This is the current term. I can just keep following all that arithmetic. I think I'm missing a parenthesis here then. Right, so we're going to add a single term. That term will be the arithmetic, current term's coefficient times the current term's exponent, and the exponent is the current term's exponent minus 1. We just keep on adding those, and then keep walking current term. This current term's next. Eventually when we're done, we'll return the result. I should be able to differentiate. So I should have 42x to the 6th plus 24x to the 5th when this one's done. 42x to the 6th plus 24x to the 5th, looking good so far. And then integrate is just the reverse of that one. Right, so we can define integrate. And again, we're just going to ignore C here, right? So define integrate. So again, I'm going to have the result, same idea here, but I'm just doing the arithmetic in reverse. So the coefficient then will be the coefficient divided by the exponent plus 1. Right, and do that with order of operations. Right, and then my exponent goes up by 1 instead of down by 1. Right, and then, so again, instead of multiplying, I divide by that plus 1, and then I take that term plus 1. I think that works for me, right? And we just keep going to the next term, the next term, the next term. Everything, again, relying on this add single term node that we are using in all of these functions here. So I should be able to integrate and get back 0.6x to the 5th plus 0.5x to the 4th. Hey, we integrated. All right, I think that covers all of those ones, and I need equals and not equals as the last two. So if I can see if one polynomial equals another polynomial. So define equals and not equals. Now, we've got a couple options here. The option that I like is the one that cheats a little bit here. Because I already wrote string, right, I can turn myself into a string, other into a string, and see if my string's equal. Those should be equivalent polynomials. So I'm going to return string of self equals string of other. And then for not equals, I'm going to return not self equals other, right? Once you write one, you have the other. So I think this cheating here is fine because I'm going to compare my strings, right? That'll be all of this string notation here. Now, again, this is a little bit ugly because I'll be adding negatives, but that's probably fine. I could change this plus sign to an equal sign if I wanted to look at the next here. If I wanted it to be a little bit cleaner, then I could just subtract. That's probably the better approach. So maybe we'll do that, and that'll be a little bit nicer here. So I'll have this string here of like that, and then we can say, hey, if my current node's next is not none, right? If it's not none, then I can check if the current node's next dot coefficient is greater than 0, right? Then I can add the plus sign, my result plus equals plus sign, so I'm going to add something because I have an next term. If it's less than 0, right, so an elif, if it's less than 0, I want to add the minus sign. right? And then if it is 0, right? So if it's not greater than, it's not less than, it must be 0, I can clean that up. Because if I have a 0 coefficient, I'm just going to ignore it here. So if it is 0, I'm going to cheat and go one more next. Right? I'm just going to ignore it as I go, because I don't want the next term, or I guess really, I just do nothing, probably. I just do a plus, I just do a minus. It's probably fine, and then I can ignore it here, maybe? I'm trying to think of where the best place to ignore it is. Yeah?
Well, there's a mistake here that I just noticed that I made when you were saying, so I went to fix it. Could you please go back to multiply?
Multiply? Yeah, so when we multiply, we're taking all of my terms times all of their terms. So I have a loop inside a loop. So I'm going to start with my first term, and every time I start, I'm going to start with their first term. So that way, when I'm looping through theirs, I will always be the first one here, so that when my term goes to the next one, I reset to their first. Right? It's my first term times their first term times their second term times their third term times their fourth, whatever. Here, then my second term times their first times their second times. So I want to reset to the first. That's the nested loop.
I noticed it was wrong because I was taking a look at my results. Because I remember you saying that we must multiply every member by itself, right? So if I multiply like 4 polynomial by 4, it should be at least 16, right?
No, because you're going to combine like exponents.
Yeah, right, okay.
So it'll be at least 4, right? Depending on what my exponents is. I think it'll be more than that. Again, it depends on what those exponents are and how they get multiplied, right? Because they're going to combine.
Okay.
So if they're, I would just have to sit and think for a minute and come up with some examples to get different lengths or figure out what the length should be.
Because like I was testing here and I noticed it was wrong. So, because what I was doing is we have nested for loops, right? I'm sorry, while loops.
Yeah.
So we have while the polynomial 1, while polynomial 2. So the first one of the polynomial 1 multiplies by all the polynomial 2, and then it keeps going. But what I was doing wrong is at the beginning I was doing like, so terminal 1, I was unpacking them like together. So eventually, if the first one is smaller than the second one, it will like break before it should, right?
Okay, yeah, that's where you get into trouble if you're not managing the combination. So all of the work for that happens in my add single term node,
Right.
where I manage all of that. If you're trying to manage that separately and then doing multiplication and seeing where it needs to land, it gets to be really messy. So I like this approach that this manages all of that for me. Because once I know how to add one term to a polynomial, I'm just always going to add one term to a polynomial for managing my results. And I don't have to try and track that inside and multiply and figure out what those exponents ended up being and where they need to go in that position. That's all.
No, what I'm saying is, I managed to fix it. Like,
Nice.
Can I
Okay.
show it to you? Would you mind?
Yeah, after when we're done, let me finish the solution and we can take a look at it. Yeah. So if you got it working and you found the fix, that's awesome. I'm happy with that. Well, we can take a look after and see where it is. So I think we're about done, right? The last piece here was just the equals, which again, I'm just abusing the string because I can compare one string to another here. Right? I don't want to bother looking at what the actual terms were. Now this is probably not exactly proper because I was rounding to 2 decimal places. So maybe that's a little bit off, that I shouldn't use string. Okay, I feel a little bad now. So maybe let's not use string then, because that was a bit of cheating. So that's okay. So we're going to start looking at all of our terms and all of their terms. So we're going to say my current term is self.firstNode, and other current term is other.firstNode. And while the current term is not none, and the other current term is not none, and as long as I both have terms, I can keep on going. So if my current term's coefficient is equal to the other current term's coefficient, and my current term's exponent is equal to the other current term's exponent, then I'm going to keep going. If they're not equal, right, then I want to stop. So really my else here at this point, then I'm going to return false. If they are equal though, right, so if they are equal, then I'm going to walk. My current terms equals the current terms next, and the other current terms is the other current terms next, because those were fine. Right, so keep on going. As soon as I find one that don't match, return false. If I've gone through all of this and I haven't returned false, now I'm only going to return true if they both are none. right? If one is none and the other is not none, I have more terms. So they've all matched, but I stopped checking because that. So now I'm going to return current term is none, or is none, right? Is none, and the other current term is none, right? Because if they did match, I go to the next one. If they did match, I go to the next one. If they did match, I go to the next one. If one of them stops being none, the whole loop stops because I can't compare a none to something else. So then I'm going to look at they both are none, right? If one of them is not none, then this will be false because they can't match because they have more terms. So I think this will probably be a little bit more proper and not abusing string which rounds, which will give us a more exact result. As otherwise I would have said rounded coefficients matched when you might not have the exact coefficient here, right? So this will be a more precise check here to make sure that something to the third or fourth decimal place different in coefficients does not come up as equal just because they showed it the same as strings. So I think this is probably better. And I think that then covers my term node class, my polynomial add, polynomial multiply, polynomial differentiate, polynomial integrate, polynomial string, and polynomial equals and not equals. Whew, yeah.
I think that I noticed, I'm sorry, when I was listening, I don't know if you did it.
That's all right.
So, what I noticed it, if you derive one and then integrate it, and one of the elements is like just a coefficient, you miss it. So what I managed to do in mine was like to create a constant of integration. So like when I integrated, I put the C at the end.
Yeah, so we're just pretending we're ignoring the C essentially.
Okay.
So, but if it gets down to the power of 0, right, we start dividing by zeros, we're going to run into trouble, right? Because when you divide by, or really that'd be the -1, right? Once your coefficient exponent became -1.
No, because you have then you have x squared plus 3. The derivative is 2x only, right?
To the 1, right? Yeah, we're not cleaning up to the 1, but
Well,
we could.
You lose the 3. If you integrate this result, it will give you x squared plus 0. So that's why like there's the C, which is the constant of integration. Because if you would lose it.
Yeah, you'll lose it when you multiply, when your coefficient, when your exponent was 1, I'm sorry, when your exponent was 0, right, you would lose the coefficient when you do the differentiation.
Yeah, differentiation, yeah. So
Which I think is correct.
Yeah, it is correct. But like if you differentiate what you derived, I'm sorry, if you integrate what you differentiated, or if you just integrate something randomly,
yeah.
You need, am I supposed to add the C at the end?
No, we're going to ignore C because we just said, hey, the constant was 0. We don't care about the constant essentially. So with the real math, you do need that so you don't lose stuff, but we're just pretending. We're going to be approximate at this point here. And I think that's fine. So if you added it in, that's nice. You didn't lose it? Sure. I just wasn't concerned at that point. So cool. Yeah, so I think that covers the project. Let's save the, because we still had our priority queues. So let's save that for Thursday. And I think we can call today good. Yes, we'll do priority queues on Pi Day. Happy Pi Day coming up on the 14th. Super excited for that. This won't be too bad. So priority queues are a special kind of queue that uses the tree structure that we've looked at. So we're going to combine the idea of a queue with our tree structure to give us this priority queue, which is a special kind of queue, which is lots of fun. Should be pretty good. And then we got to talk about the next project. So I did post that here. So the next project uses stacks and queues all the way back from here. So I went to the linked objects first, and then we're going to come back. Now we're coming back to stacks and queues because we're using queue. We're not going to use a priority queue. It's just a regular queue. But that wraps up. This will be the last individual project of the semester. So this will be due the 26th. We'll pick up our final project on the 26th. Then we've got the rest of the month of April to work on, essentially the end of March and the rest of April to work on for a final project coming up. That'll be the last individual project, the final project. We should do in pairs. So if we look at our outcomes here, I think this is where we got this from. One of the outcomes here, let's see where it is here. Write a medium-sized program as part of a team. Now, team is a bit of a stretch because I'm only going to do pairs. If it doesn't work out and we need one group of 3, we can do one group of 3. But really pairs is better, just pairing up with somebody. And a pair is a team. You're working with someone else here. So that one is a requirement. We can't do this one individually here, because this is one of the things we need to assess, is that you can actually work together with somebody, which works out. And you generally get a better result as long as your partner doesn't just ignore you, which has happened. And at that point, I will fire your partner, and you can find a new team or partner, join a group of two. But you've got to at least try to reach out to them. If they don't get back to you within a week, right, we're just going to drop them and say, all right, it won't work. So you have to work with somebody, right? Ideally, I mean, you had no idea we have an option for remote, and you came into the class, so I'm expecting everyone to come Tuesdays and Thursdays, and you can talk to your partner. If you're both okay doing remote, great, that's fine. We do remote work in the world all the time nowadays, and it works out great. But if you start ignoring your partner and don't respond to them within a week, I'm dropping you. If you don't finish the final project here because you got dropped, remember that is worth 40% of your score. You cannot pass the class, right? You fail the class because you don't have that 40% of the score. So you have to be a good partner here. And I'm talking to everyone on the video here because you're not here, and that's okay, that's an option. But if you're going to do that, you need to be a good partner and be responsive. So heads up, coming up the end of March, all of April, good partners, yeah.
What is it going to be on?
Probably blackjack. I've got to double check, but probably you're going to do some blackjack analysis and simulations and coming up with what do we think makes a good winning strategy. It gets to be a little bit of fun. That one or poker, I'm trying to decide still, but probably blackjack. I like that one. All right, so the last individual project on stacks and queues. This one is just us exercising the stack and queue in the library. You can use the one we wrote in class. You can use the one in the library. I don't really care. The idea here, though, is that we actually use stacks, we actually use queues, so we're forced to only be able to access the value at the top of the stack or the front of the queue, right? We're forcing ourselves into that because it fits for this solution, and it's good practice using it here. So this is just a very contrived example here. I stole this one from Dr. Ellenbogen, and I like it as a silly example of using stacks and queues. So it takes a second to wrap your head around. So we'll go over it here, and we'll talk about it. So we are loading airplanes and trains from containers that come from ships. That's the idea here that will set the stage here. So a ship comes into the dock, we need to unload the ship. It knows here's all the containers that go on trains. We're going to unload all the train containers, and we're going to unload all the plane containers. Right? So on the dock, we can stack them up to 5 high to go on trains. When we start unloading the ship, they go in 5 high stacks. From there, we'll put them on trains. Right? OSHA requirements are safety requirements. You can't put containers more than 5 high, otherwise they'll fall and crush somebody, and you can't kill people at work, otherwise you lose lots of money. And it's a bad thing, but businesses don't want to kill people at work because they lose money, right? And it's a bad thing. But again, money drives all these things here because we live in a capitalist society. So when we send things by plane, we just put them on an assembly line. Essentially, we've got this big old conveyor belt that heads out to the airport. We're close to an airport, we can just put them on a conveyor line, they'll just go. Hey, that's a queue, right? In an assembly line, the first one on is the first one that will get there. We'll take care of that. They are labeled based on the train number or plane number. So train number 1 containers, say train number 1. Plane number 2 containers, say plane number 2. So I know what plane or train they will end up on because it's labeled on the container, right? So planes on the assembly line, we assume one worker is loading trains and one worker is loading planes. So the trains loader from the dock grabs their high-low, grabs a container, puts it down, grabs the next container, puts it down, grabs the next container, puts it down. Once I've got 5 containers, I go to the next one. I start loading in front of that one. So these essentially have been put in a stack that are in a queue, which is fun as we kind of visualize that. Yeah?
Oh, sorry. So, okay, we have a ship that is loaded, okay? We need to unload the ship.
Yep.
And load these same containers on different airplanes or
planes or trains. Yep.
So like the last one here, actually the first one that is being loaded, the ship, will be the last one to be loaded on the airplane.
So if it's a plane one, it will just go on that queue, that assembly line. So the last one pulled off will be the last one that goes on of a plane. Trains are a little different. So trains end up in stacks of 5. So we're going to stack them 5 high, and then we'll do another stack 5 high, we'll do another stack 5 high, we'll do another stack 5 high, but the front stack will get worked first. So the train items are going into a queue of stacks. So we're putting stacks of items in a queue that we're going to work. We work the front first, right? You can't get to the ones behind once you've loaded them here. So we'll draw a picture in a second. That'll help it here. it's a little easier than the text. But again, we're going to work through it. It's kind of fun.
It's interesting.
Yeah, it's a thought exercise, right?
It seems to be hard.
It won't be too hard, I promise. It comes up pretty quick. So when we load items from the dock to the train, so the unloading piece happens, and we've got them loaded. What we're tracking now is once it's been taken off the dock and readied, how long will it take us to load these things onto the trains and planes? So the worker who loads things from the queue of stacks for trains takes 2 minutes per train number to get the item from the dock to the train and come back. So they pick up whatever's at the top of the front stack, say, oh, it's for train number 3. They go to that train number 3 with the item, and then they come back. That took 2 times the train number to get there, because trains are further apart. Sure, right? The closest train takes 2 minutes to get there and back. The next train takes 4 minutes to get there and back. Train 3 takes 6 minutes to get there and back. Sure. So what we need to track then is how long it takes to load all of the materials. For planes, it's 10 minutes times the plane number. The airport's a little further away in this conveyor belt here that we've been working on. We've taken the front item, it's just a queue, the front item to that train, that plane, and we come back. 10 minutes round trip, right? So the input here is very text-based here. This is the input. The idea here, this is an example sort of problem like you'd get in the ICPC programming competition, which is once you take 350, generally that level or higher, you can do the competition. We used to send a team every year. It got a little weird during COVID, and we're not sending teams anymore, but it was fun. But this is that input.
You used to send teams?
Yeah, we used to send programming competition teams. Yeah, it was fun. I went 1 year with the team, and Dr. Allenbook couldn't go. So 4 integers, the trains and planes, number of trains and number of items for trains, number of items for planes. So how many trains there are, how many planes there are, the number of items you have for trains, the number of items you have for planes. So 3, 2, 10, 5 is 3 trains, 2 planes, 10 items for trains, 5 items for planes. That's the first line. The next line is how many items for each train. The next line is how many items for each train. So train 1 gets 2 items, train 2 gets 7 items, train 3 gets 1 item. Plane 1 gets 3 items, plane 2 gets 2 items. The next lines are how many, or what train the item is. So when these were pulled off the dock, the first container was for train 2, the next container was for train 2, the next container was for train 2, the next container was for train 1, the next container was for train 5. Remember, we're putting these in stacks of 5 high in a queue. The next item was for train 2, train 2, train 2, train 1, train 2. Right? There was 1 item for train 3, that was right here. There were 7 items for train 2, 7 twos in this list here. There were 2 items for train 1, train 1, train 1. So we have to load these into the stacks of 5 high in the queue, right? And then items for planes, 3 items for plane 1, 2 items for plane 2, right? Plane 2, plane 1, plane 1, plane 2, plane 1. These items went in here. Then what we're going to output is how long it took to load each train on one line, how long it took to load each plane on one line. So this is where we're going to draw a picture. Right? So drawing the picture really helps here. So we put this to one side here, and my browser to the other side here. I'll shrink that down. So we have train 1, we have train 2, we have train 3.
You all have 3 trains.
3 trains, right? 3 trains here. There are 10 items total. Train 1 is going to get 2 items, so this needs 2 items. This one needs 7 items, this one needs 1 item. Yeah?
Just make sure, what exactly is 3 cheap than 5?
3 is 3 trains, 2 is 2 planes. 10 is 10 items for trains, 5 is 5 items for planes. The next row then is train 1 gets 2 items, train 2 gets 7 items, train 3 gets 1 item. Then I have planes. I have plane 1 and I have plane 2. That's a P, sorry. Plane 1 gets 3 items. That's this value here. Plane 2 gets 2 items. That's the next value here. Yep. Then this is all the items for trains. Then this is all the items for planes. Okay. So I'm going to be stacking these items 5 high. So I'm going to have a stack of 5 high. So I'm going to get 2, 2, 2, 1, 3. Right? These are my train items. They get stacked 5 high in a queue. My stack is 5. Now the next train item goes to the next stack. So now I get 2, 2, 2, 1, 2 from this row, this line. The 4th line is all the train items.
But what is true one?
Train 2, train 1, train 3. Right? This is the train number. So train number 2, train number 2, train number 2, train number 1, train number 3.
What is that for?
To tell me which train this container goes on. Right, I've got 3 trains. I have train 1, train 2, train 3. These are which train that container goes on.
Okay,
Right?
so train 2 will get what?
We'll get 7 items. There's 7 2s in this list of train items as I pull them off the dock. Right, so the dock worker is putting them in stacks in a queue. So here's the queue, right? You can only get the front of the queue. Here's your stack of 5 high. Here's your next stack of 5 high. Right? If I had more items, I'd have another stack here. Right, I would just keep going. Right? Then my train loader will take the top item off the stack, right? Because it's a stack here. They will take the item for train 3. So my timer starts with the train worker. So I've got my little train worker here, right? He starts at 0 minutes. At 0 minutes, he grabs the first item. Says, oh, it's for train 3. He goes to train 3. That took him 3 minutes to get there because it's 2 times the train number for a round trip. So it's 1 times the train number to get there. Drop it off. This train is fully loaded 3 minutes in. It only had 1 item. It is loaded 3 minutes in. It's done. Finished. He comes back and it's been 6 minutes. Right? The next item he grabs, right, that one's done, is train 1. He goes and loads train 1, goes and takes it to train number 1 for 7 minutes, comes back and it's been 8 minutes. He grabs the next item, train item 2. He goes, it takes train number to get there. So it has been 8. Right? It was 8. Now, to get to train 2, it's been 10 minutes. He comes back and it's been 12 minutes. That one's done. He grabs the next item. It's been 14 minutes. He comes back and it's been 16 minutes. That one's done. He goes back again. It's been 18 minutes. Comes back, it's been 20 minutes. That one's done. The stack is empty. Now I can grab the next thing in the queue of stacks. The next one now is for train 2. So it's been 20 minutes, then 22 minutes to get there. Come back, it's been 24 minutes. Here's what I have for train number 1. I get there, it takes me 25 minutes total now. Train 1 is fully loaded, right? Train 1, now it took 25 minutes to get there, to load it. Train 1 took 3 minutes. Train 1 is 25 minutes, right? I come back and it's been 26 minutes. I grab this one for train 2. It's been 28 minutes. I come back, it's been 30 minutes. Grab this one, 32 minutes. Come back, it's been 34 minutes. I take this one, load it up. It's been 36 minutes to get there. Here, train 1 is loaded in train 2 is loaded in 36 minutes. 36, right? Because it took me 36 minutes to load that train. Now my trains are loaded. So my output for trains, right? Train 1 took 25 minutes, train 2 took 36 minutes, train 3 took 3 minutes. So 25, 36, 3 was my output for trains. That was trains. Now for planes, I just take these items and put them in a queue. So 2, 1, 1, 2, 1. To load these things. I'm going to work the front of the queue. It takes 10 times the plane number to get there and back, so 5 times to get there. So plane 2, this one takes me 10 minutes to get there, 10 minutes to come back, it's been 20 minutes. That one's done. 5 minutes, 5 times the plane number to get there, 25 minutes to load this one, 30 minutes to come back. Grab my scroll bar, right? And then this item. So 35 minutes to get there, 40 minutes to come back, that one's done. And then 50 minutes to get there, 60 minutes to come back, 5 times the plane number to get there, 65. So plane number 2 is loaded at 50 minutes in. Plane number 1 is loaded at 65 minutes in. So 65 and 50 for my output. And then I've done loading. So trains will be loaded 25, 36, and 3. Planes will be loaded 65 and 50 for this given input. Now, specifically here, 0 or more trains, or I'm sorry, 0 to 100, 0 to less than 100 trains, 0 to less than 10 planes. So you can have 0 planes, or you could have 0 trains, right? You might have then 0 to some number of plane items, some number of train items, n number, as big as it wants to be, perfectly fine, right? Based on number of train items, number of plane items, right? There's no bound on that one, right? But 0 to 100 trains, 0 to 10 planes for a bound. Right, so that's the next project. Planes and trains, working with some silly numbers here, getting some output, working on that one. All right, that's all we got today. We'll meet back up on Thursday. We'll talk about priority queues.